Illustrative Math, Algebra 2, Unit 2, Lesson 4 is called Combining Polynomials. Our learning goal today is I can perform operations with polynomials such as addition, subtraction, and multiplication. And then I also understand that the result of these operations on polynomials will always be a polynomial. That idea right there on the second part of the goal is actually, there's a name for that. It's actually called closure. All right, our book does not use this word, but that's what it's called, closure. Polynomial times a polynomial is a polynomial. Polynomial plus a polynomial is a polynomial, and so forth with subtraction. Okay, what do you notice? What do you wonder? Pause the screen and go ahead and write some things down. Okay, so some things that you might notice. Let's see here, if I can write here. All right, first thing, all problems have 7 and 9. I would say the last problem has a non-integer solution. Okay, integers, again, remember if you need a refresher on what an integer is, integers are 0, 1, 2, 3, and then it goes on forever. And also the other direction, -1, -2, -3, ... goes on forever. So both directions, no partial numbers, whole numbers and negative whole numbers. Let's see here. What other things might we notice here? We have 4 different operations. All right, so these are maybe notices. Let me go up here. Okay, some wonders. Will the 7s repeat forever? What else? Why are there only integers? No decimals, really? For the initial problem, I guess, only integers in initial problem. Why is the last answer not an integer? Okay, that's the big one. So I guess leading into the lesson without ruining it for you is when you look at these 3 here, we have integer times integer equals integer. Integer plus integer equals integer. And integer minus integer equals integer. Okay, and then over here we have integer divided by integer equals non-integer. Okay, so addition, subtraction, multiplication have closure for integers. Okay, that's what we're going to learn about today. All right, so let's kind of go through these and see if we have closure here. So which of these statements are true? Give reasons and support. If you add 2 even numbers, you always get an even number. So what I'm going to do is I'm going to try a few of them and see if it works. Even plus even equals even. That worked. Let's try another one. Even plus even. Yep. Maybe even a negative even. Looks like it's true. Now, I didn't prove that it's true, but I would have a strong hunch that it is true. So I would say this one is true. Next one. If you subtract an even number from another even, you always get an even number. Well, let's try a couple. Even minus even equals even. That works. That works. And then try some negatives. Negative 10 minus negative 8. So that becomes plus 8. That gives me negative 2. It looks like they're always even. I'd say that's true. So if you add two odd numbers, so 3 plus 5, that gives me an even. So this is what's called a counterexample. We only need to find one that does not work. If I find one that it's not true for, then I can say that this is false. Okay. Subtract an odd number from another odd number, you always get an odd. 11 minus 3, that equals 8. So that's a counterexample, so that's false. If you multiply two even numbers, you'll always get an even number. 2 times 4 is 8. 6 times 10 is 60. Negatives aren't really going to change anything. So this one looks to be true, I think. We don't know. We didn't prove it, but we have a strong hunch that it is. If you multiply two odd numbers, you always get an odd number. So we're going to try a couple. 3 times 7 is 21. 9 times 9 is 81. 7 times 5 is 35. Looks like it's true. Can't find one that doesn't work. Number 7. If you multiply two integers, you'll always get an integer. I think that would be true. We don't need to go through all those. You learned your times tables back in grade school, and you know that you always had integer times integer equals integer. Same thing here. If you add two integers, you always get an integer. I would agree. And then last one, if you subtract one integer from another integer, you always get an integer. That is true. Okay. One of the numbers would have to be a decimal or a fraction to get a non-integer solution. Okay. All right, here's some questions about polynomials. If you add or subtract two polynomials, you will always get a polynomial. So I'm going to just do this. I'm going to make up some polynomials here. So I'm going to go with 3x squared plus 2x minus 4. That's my first polynomial. And I'm going to add another polynomial. I'll make this one that. Okay, so really it's like this polynomial plus that polynomial. Okay, I'm going to just get rid of my parentheses though. And I'm just going to basically combine like terms. So I only have 1x to the fourth term. I have a 3x squared plus a 3x squared, so I add those and I get 6x squared. I got a 2x and a 5x, so I add my coefficients and I get 7x. And then these are my constants. Negative 4 minus 1 would be negative 5. Okay, so there's your answer. So that's a polynomial plus a polynomial. Looks like it's still a polynomial. All right, maybe try another one. Let's say 2x squared plus 6x minus 1. Let's do minus. I don't know. Let's just go x plus 6. Now here I got to actually distribute this negative. So I'm going to change those. And then I get 2x squared. If I combine these, I get plus 5x. And these are minus 7. So So there you go. That's still a polynomial as well. I don't have any negative powers. I don't have like division of x or fraction exponents. So this is a polynomial as well. So I'm going to say I think this is a yes. Okay. If you multiply two polynomials, all right, there's my two polynomials that I'm going to use to multiply. I'm going to use that box method. So I put my terms right here. And what I do is I create a little box. Whoops. That's a circle, not a box. Okay, and I'm basically going to multiply these. So x times 3x squared is 3x cubed. X times 6x is 6x squared. 3x squared times 3 is 9x squared. And then 6x times 3 is 18x. Now I got to combine like terms. So I have 3x cubed. I have 15x squared plus 18x. Looks like it's still a polynomial. Now I could go ahead and do a few more of these. Maybe try one with 3 terms. Okay. But if I keep doing it, I'm always going to get a polynomial. Maybe you could try a couple on your own. Maybe try something like this: x squared plus 4x minus 3, something like that. Polynomial times polynomial. Do your box method, combine like terms. Your final answer will always be a polynomial. All right, so what was something you found out that was surprising today? I guess I would say that, I don't know if it's surprising, but I'd say something that you found out today is that polynomial addition, subtraction, and multiplication results in another polynomial, similar to how integers work. What was difficult about doing arithmetic on polynomials? How'd you feel with the difficulty? I would say it is a little tedious because you can do it in your head. You need scrap paper, you need to make a box, you need to stay organized. But I would suggest stay organized. Use a box, underline like terms, etc. Now, what do you think would happen if we divided one polynomial by another? Would we always get a polynomial? All right, so the answer to this is no. The reason I say no is because we saw on the warm-up with division, I'll go back to the warm-up slide. We saw right here with division, integer divided by integer does not give me an integer, but multiplication, addition, and subtraction does. So it's probably going to be the same for polynomials, okay? So integer divided by integer does not always equal an integer. So I am going to assume that it works the same for polynomials. Okay. And if you wanted me to draw an example here of polynomial division. Um, we could do one. It would be something like this, maybe like 3x squared plus 2x plus 1 divided by, I don't know, let's say x plus 2. All right. And basically, we haven't really worked on how to do division yet, but you can't cancel things. You can't cancel these twos. This is like one whole term. So you can't end up canceling it. So you now end up with a non-polynomial because we have this x plus 2 in the denominator, if that makes sense. Okay, on to the next slide. All right, back to our goal. I understand that if you add, subtract, or multiply polynomials, you get another polynomial. So here are two expressions whose product is a new expression, A. What can we put in boxes to make A be a polynomial? Okay, what are some things we could put in there? Well, this would have to be any real number, really, for this first box. So we'll call this box 1, call this box 2. So box 1 can be any real number. The coefficients don't matter. But box 2, you have to have whole number exponents, okay? So box 2 must be a whole number, okay? Whole numbers, if you don't recall what whole numbers are, I'll draw them right up here. Whole numbers are 0, 1, 2, 3, dot, 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 okay? So no fractions, no negatives. You have to have whole numbers. What can we put in boxes A to make it not be a polynomial? So really, all you need to do there is put in a fraction or a negative number, and that would make this not a polynomial. Okay, so we'd have like here in, well, I guess a fraction or negative number in box 2. Okay, I guess in box 1 you could put a new variable. If you did, in box 1, I put like, if I had negative 2x cubed plus y times x, that would not be a polynomial. If I put a negative number here, like a -1 or any negative there, that would also make that not a polynomial. All right, hope you enjoyed today's lesson. That's about it.